Okay. So hi everyone. Good morning, or good evening, good afternoon, good night, wherever you guys are around the globe. So it's really nice to be here, even if just virtually with all of you. I wish I could have been there in person, and I hope you guys have been enjoying your time together, and that everybody in your household and family and your loved ones are safe and healthy. So I was asked to talk about strongly interacting massive particles. In short, these are called SIMPs. And we're actually going to do a little bit more than that. We're going to be talking and learning about SIMPs, cannibals, and elders. So it's really nice to meet you guys. And the rough plan for our time together. So we have two 1.5 hour lectures that we're going to spend together. And what I really hope to do in our time together is give you sort of a taste of what I think are really exciting developments in dark matter, which I know you've been hearing about other aspects throughout this school. But I really want to give you sort of a little bit of tricks of the trade, methods, give you a little bit of a sense of the type of things that I feel it's much more difficult to get a grasp for if you're just reading papers or reading lecture notes, to really sort of give you a little bit of a sense of sort of how to quickly get interesting results and understand what's going on. And so throughout this time together, I'm going to be dropping order ones. We're not going to be following through with factors of that sort. You're going to be able to see how to put those things back in, but I really want to give you a sense of how you do quick back of the envelope estimates to understand some really big picture interesting stuff. Okay. And in order for us to sort of do this together, here's the outline. So I want to make sure that this course is really self-contained. So at the beginning, I'm going to start off with setting the stage. Okay, so we're going to do a little bit of early universe cheat sheet. I know that this might be stuff that you're somewhat familiar with. I want to make sure that I'm going to give you guys everything that we're going to need in order to move forward together in this course. And then we're going to look at 2-to-2 processes. We're going to work through the WIMP in a very particular way. I know that you guys have been learning about the weakly interacting massive particle already. I want to phrase it in a particular way that's going to be very useful for us. And then we're going to move on to the main thing that we're going to be talking about, which are 3-to-2 processes. And here we're going to see SIMPs. We're also going to see cannibals. And we're going to see elastically decoupling relics, elders. Okay. And then towards the very end, we're going to move on to talk about dark sectors and how all of this picture sits together. Okay, so I'm imagining that today, most likely, I anticipate we're probably going to get, I hope, sort of towards SIMPs, and then we'll be talking about cannibals and elders and dark sectors tomorrow. Okay, and the other thing that I'm gonna throw out there before we really delve in. So I'm gonna put out here. I'm just gonna address the crocodile in the room. It's right over here. So I'm gonna call this the crocodile challenge. So I love crocodiles, and it's been a lifelong dream of mine to have a paper which could have a crocodile Feynman diagram in it for like scientific reasons. I have so far epically failed, but it would be really awesome. And I give you guys this challenge: if maybe one day when you invent a new dark matter model or some other model or theory in particle physics, if you could figure out a way that there's a crocodile involved in it, I would be extremely grateful. I'll be eternally grateful. And if you could drop me a line if that ever happens, it would be really, really super cool. And tomorrow I'm going to show you guys the closest I've ever gotten to addressing this crocodile challenge. Again, so far I've failed, but maybe by the end of the course, one of you will have succeeded. Okay, so let's start at the beginning and let's set the stage. So obviously you've been learning a lot about dark matter. Let me just give you sort of the first few bullet points on this topic. From our perspective, as we know, the universe is dark. That's no surprise. We also know the amount of dark matter that we have in our universe, nearly 30% of the energy content. For our purposes, the way that this is going to be convenient to represent is the fact that the energy density of dark matter is roughly 5 times that sits in baryons. Okay, so we're going to be using this sort of as a stand-in for that 0.3 GeV per centimeter cube that you're probably more familiar with. As a reminder, we know that dark matter is massive, but we have absolutely no idea what its mass actually is. You probably saw something like this in Josh's lecture in the first week. If we look at what's the mass of dark matter, well, there are some 80 orders of magnitude in which the mass of dark matter can reside. It could be roughly as big as 10 to the 50 GeV, or even as small as 10 to the minus 30 GeV, where on one side we run into problems from microlensing, and on the other side, dark matter is too fluffy, just the wavelength exceeds galaxy size. So here it's too fluffy, okay? And we have absolutely no idea where it is, 80 orders of magnitude. And we really want to be able to nail this down in a more concise manner. What we know about dark matter is also that it shouldn't interact too strongly with QED and QCD, because otherwise we already would have detected it. So it shouldn't interact too strongly with known forces, QED and QCD. We also know that dark matter shouldn't interact too strongly with itself, because strong self-interactions distort dynamics in dark matter halos. Although this is also a potential signal of dark matter, which we're going to be addressing tomorrow. So it shouldn't interact too strongly with itself. Okay. But as I said, this is also something that is potentially a signal for some models of dark matter, and we'll be discussing that tomorrow. And very importantly, of course, we wouldn't be here without it. Okay, so the fact that we're even here asking the question of what it is really strongly depends on the fact that it was even here to play its important role in early universe dynamics. And so what we're out to answer overall is, what is dark matter? What is it? And in particular, what are the mechanisms in the early universe that can set its abundance, so to set its relic abundance. And once we do this, we want to do model building to understand exactly which type of theories would admit these types of behaviors. And of course, we want to understand how to detect it and what are the constraints that already exist, okay? And so I hope we're going to be trying to answer these questions in the particular context of these 3 to 2 interactions, which we're going to be discussing together. So let's start with an early universe cheat sheet. Okay, so this will really, everything we're going to need to know about the early universe. Early universe cheat sheet. Okay. So as you know, our universe is expanding. So here's our expanding universe. Oops, universe is expanding. And that means that if I have some length L, then it's going to expand to be some other length. It'll be A times L, where A is the scale factor. And that means that our volume expands like A cubed. Okay, and if we take some line element, so here's, let's say, some ds squared, which is dt squared minus A of t, that expansion, squared dx squared, then we can define Hubble, the Hubble parameter, which is A dot over A, in other words, dA dt, 1 over A. So this is Hubble, which is going to be appearing all over. And importantly, from the first Friedmann equation, in the absence of curvature, we know that h squared goes like rho over 3m Planck squared, and rho, which is the energy density, is just a black body radiation, so it goes like t to the 4th. And so Hubble, and this is what's going to be important, Hubble is going to scale like t squared, temperature squared, over m Planck. Okay, so this is going to be one type of scaling that we should remember throughout the course together. Our early universe is a thermal environment. Early universe is a thermal environment. Okay, and that means that we have phase space distributions for species that are in thermal equilibrium. So we have phase space distributions. Let's call it, let's say, F, an equilibrium of momentum. And from this, we can integrate and get the energy densities and the number densities. And that's what we're going to care about for today. So we need the number density and energy density. okay? And sort of, again, just the ballpark, because we're not going to care about the order ones here today. But when the species are relativistic, the number density scales like temperature cubed, okay, when the species are relativistic, and rho, the energy density, scales like temperature to the fourth. So this is going to be the scaling that we should all try to remember together. And when things are non-relativistic, the number density gets exponentially suppressed. So it goes something like, again, I'm dropping order ones, mass times temperature to the 3/2, e to the minus mass minus chemical potential mu divided by temperature. So this is when I'm non-relativistic, when the temperature is much smaller than the mass of the relevant particle. And the energy density, which is just mass plus 3/2 temperature times n, this is just going to go like the mass times the number density. Okay, so when species are non-relativistic, we have a different scaling for the number density and the energy density. And in particular, if I have fast number changing processes, which set the chemical potential to 0, then the number density is going to be exponentially suppressed. Okay, so in particular, when chemical potential equals 0, which means that the number changing processes are fast, then the number density is exponentially suppressed, okay? Exponential suppression for our number density. And the last thing that we're going to need is the entropy density. And entropy density is going to scale like temperature cubed, okay? This is when it's relativistic. It's dominated by relativistic species. Okay, so we have the scalings for number densities, entropy density, and energy density. And now let's write out our Boltzmann equations. That's going to be the next thing that we're going to need. So here's the Boltzmann equation. And again, just in case I don't know what exactly you guys have seen before or not, I want to phrase things in a particular way that then is going to enable us to move forward quickly together. So Boltzmann equation is telling us how the number density is evolving in time or in temperature in the early universe. So if we consider a system, let's consider at first a system with no collisions. Okay, so these are just free particles. And if I have free particles, then the derivative with time of the total number of particles is just 0, right? There's nothing happening, no change in total number of particles. But now we're going to write that total number of particles as a density times the volume. So this is going to be d density times volume dt. This is just that volume. Here's volume v. dn dt plus n dv dt. And this should equal 0. Let's just divide out 1 over v, so dn dt plus n over v dv dt equals 0. And as we said, volume scales like scale factor cubed. And so this means that 1 over v dv dt is 3 over a dA dt. And now we can plug this in down here. And what we find is that our Boltzmann equation is the n dt plus 3n a dot over a equals 0. But I remind you that this is exactly what we defined as the Hubble constant. Okay, so this is the Boltzmann equation for free particles in the absence of any interactions. And of course, if the particles are not free, if not free, then we have collisions. And what happens is that our right-hand side, it becomes all of these collision terms, and we're going to write them out for particular cases in a moment. So the n dt plus 3nh equals minus collision terms that are a function of the number densities of the particles that are involved. Okay, so this is the general form of the Boltzmann equation that we're going to be using. And so I know that you've done a lot of WIMP-like processes so far in the school, And more generally, there are many mechanisms to set the dark matter abundance. So these are the different types of processes in the early universe that set the relic abundance. Of dark matter. Okay, and so in particular, I hope that you guys have perhaps seen in Josh's lectures a couple of weeks back, the 2-to-2 zoo. So just to draw a few of these over here. So in the context of the 2-to-2, we could have we could have sort of the standard WIMP. I'll draw it like this. So chi here is always going to denote dark matter for me, and I'm always going to have time going from left to right. Okay, and so here's how the WIMP would be portrayed. It would be two dark matter particles annihilating, so chi annihilating into something. Let's call that phi. This is the WIMP. This is the standard annihilation. But of course, we could also have other types of 2-to-2 processes. So I'll just draw them out here. We're not going to be working through most of these. I could have chi going to phi, the exact same thing, except look at a kinematic regime where the incoming mass is smaller than the outgoing mass. So this would be a forbidden process. So this is forbidden dark matter. I could have semi-annihilations. So again, 2-to-2 process where I have two chi's coming in, only one chi coming out, and something else. So this would be a semi-annihilation process. We could have co-annihilation, so that looks in the following way. It's some tower of particles, of dark matter particles that are coming in and annihilating into stuff. And this is also a possibility for setting the relic abundance of dark matter. We could have co-scattering. So co-scattering, again, always 2-to-2. Here's chi, here's some other particle, some other light bath particle that it's scattering off of, and changing its identity to some other dark particle, psi. So this would be co-scattering. I don't know if you guys saw with Josh, there's also something called zombies. So I could have a chi that meets a phi, and the phi eats it and makes it into a phi. That's why it undergoes a zombie process. I don't think when it got published in PRL, they were allowed to keep the word zombie in the title, but I'm not positive. And importantly for us, there's also something kind of surprising, and we'll see how this happens, where dark matter scatters elastically off of some other light particle. Okay, so it's just an elastic scattering process, and this is the process that controls elastically decoupling relics, elders. And so these are just examples of the 2-to-2 zoo, and hopefully some of these, at least you've worked out in your lessons with Josh. We are going to be working through this elder. We'll understand this, but that's going to happen sort of tomorrow. And the one that I want to focus on now is the very well-studied WIMP, but I want to phrase it in a particular way that's going to be useful to us. Okay? So let's talk a little bit about the WIMP. Okay. So it's no secret, I think, that the star of the show for the last 40 years basically has been the WIMP. Okay. So this has been the star of the show. For probably 40 plus years. Okay, so this is the process that we're talking about. Chi goes to phi. Okay, so let me just draw that over here. Okay, and I don't care how this is happening. That's why we draw this blob in the middle. We're talking at the mechanism level, not writing down particular models that give this behavior. Okay, so here is our annihilation process. Okay, so that's how time is going. Now, if this process is very fast, then it's a number changing process. It's going to set the chemical potentials of chi and phi to be the same. Okay, so if fast, this is going to set chemical potential of chi to be equal to the chemical potential of phi. And here's our Boltzmann equation that describes it. D nx and chi, dt plus 3 n chi hubbo equals minus the collision term. Okay. Now, as a side note, I want to point out already now that, you know, if I have this diagram, then of course I also always have, I can take the diagram and I flip it on its side. And so we always, this is a side note, we always also have elastic scattering that's happening here. Okay, so that's, I flip it on its side, and here is my chi scattering off of phi's to give me another chi and a phi. Okay, and so if we assume if this phi is some bath particle, okay, maybe it's the standard model or it's a particle that's thermalized with the standard model. Okay, so we're going to assume that phi is a bath particle. And so what this is going to do, what that means is that the chemical potential of phi is 0, okay, and it has a temperature. And so this, together with the regular WIMP annihilation, is what sets for us that the chemical potential of chi is equal to that of phi, which is equal to 0, okay? And this process is always happening, but it decouples after the annihilations decouple, okay? And we're gonna, this is gonna be relevant for us when we look at the Simp as well. Okay, so almost always, I'll just write that out here, that almost always the chi goes to phi process, shuts off before the elastic scattering of chi phi goes to chi phi, okay? And we're gonna see explicitly why this happens when we talk about Simps. Okay, so going back though to our 2-to-2 annihilation, we have the Boltzmann equation over here. Let's write down what the collision term looks like. Okay, so what's our collision term? So you can roughly think of things, a rate for some process to happen is the thermally averaged cross-section, times number densities. Okay, and so what this ends up looking like over here, and I'm sure you've already seen this equation, is that dn dt plus 3n chi h equals to minus the thermally averaged cross-section of this process we're looking at, chi annihilating to phi times, we take into account both the forward annihilation process and the back reaction production process. So times n chi squared minus n equilibrium of chi squared. Okay, so let me just explain what's going on over here. Okay, so this first term over here, this is indeed exactly the annihilation that we're talking about, chi annihilating to phi. And this term over here is meant to be the stand-in for the inverse process, where phi produces 2 chi's. Okay, so let's understand why we can write it. Why am I writing it in this way? Why can I write it as the number density of equilibrium? The reason I can do it is because of a trick, which again, we're going to be using a lot during this course. We're going to use the trick of detailed balance. Okay, so what detailed balance says is that in equilibrium, the forward processes and the backward processes are both very rapid, and things should cancel out. Okay, so in equilibrium, the forward and the backward processes are both rapid and should cancel out. Okay, and so this is the reason that we can write the back reaction in this way, because we know that in equilibrium the answer has to be 0 on the right hand side. Okay, so this is why we can write the back reaction in this way. Okay. And so we have our Boltzmann equation, and now of course we want to go ahead and solve it. And again, I'm going to draw the picture that you're all very familiar with already, but I want to make sure we understand it properly, because it's going to be an identical story when we talk about Simps and the other processes. Okay, so what happens? How do we solve this? So instead of, we're going to do the usual thing, instead of thinking of how the particle density is evolving in a box, let's think about particle densities in a box that's expanding with the universe, okay? Let's think about particle density in a box that's expanding with the universe. Okay, so this is why we move to talk about the yield, typically denoted by Y, which is the number density divided by the entropy density. So this just goes, n times scale factor cubed. Okay, so we talk about the yield, and this is what it typically looks like. So again, this is the standard picture that I'm sure you've seen many a time. So here is this yield. I'll just divide it by the measured value. Okay. And instead of talking about temperature, we often move to talk about X, right, which is the mass of the dark matter divided by the temperature. Okay, so X evolves, X large means that T is very large or temperature is very small. Okay, and of course what happens is that in the early universe, both forward and backward processes are rapidly occurring, and so the yield is basically fixed. At some point, the temperature drops beneath the mass of the dark matter particle, and then it becomes energetically very difficult to be producing the dark matter particles, and so the production, the inverse process, just shuts off, and dark matter is essentially, it's now non-relativistic, it's just rapidly annihilating away. And if this were the end of the story, it would have annihilated, all the way away. Of course, that's not what happens, because as the universe continues to expand, the particles become more and more dilute until at some point they can no longer find each other in order to annihilate. And that's the point where freeze-out occurs, and we're left with a constant relic abundance of dark matter. Okay? And of course, how much exactly we're left with is a function of this cross-section, depends on the strength of the interaction. So how much is left is a function of this thermally average cross-section of the size of our interaction. Okay? So this is the, sorry about that. This is the standard picture for freeze-out. Okay. And I went through this because literally the exact same thing is going to happen for these other seemingly more exotic processes that we're going to be discussing shortly. Okay, it's literally an identical story where at very early times we have forward processes and backward processes that are both rapidly occurring. So both, let's do it this way. So up here, both rapidly occurring. In this area over here, things are non-relativistic. The production is suppressed. And once we get to this point, things are so dilute that the annihilations shut off. Okay. So to understand, what's happening, at what point is this happening, we're going to do a back of the envelope estimate together. Okay. And there are many ways to do this. I want to do it again in a very specific way, which is going to be useful to us. Okay, so back of the envelope. When does freeze out happen? Okay, so freeze out happens roughly when the rate for the 2-to-2 annihilation that we're talking about is of order Hubble, right? Because that means that's exactly the point where the particles can no longer meet each other. Before they manage to meet each other, the universe is already expanded and the particle is not there for it to meet. So it happens when, let's call it the rate for the 2-to-2 process is of order Hubble, okay? And so the way that I want you to think about this, and this is going to be true throughout the course, is think of yourself, you're a dark matter particle. What needs to happen in order for the process to proceed, okay? So let's take a look at this 2-to-2 rate. Okay, so the 2-to-2 rate, if I'm a dark matter particle, then I need to meet another dark matter particle. So the rate is going to be proportional to the number density of the particle I need to meet the dark matter particle. And it's also going to be proportional to the strength of the interaction. That's what we called sigma v, the thermally average cross-section. And this has to be, of course, of order Hubble, which, as we said, goes like temperature squared over m Planck. Okay? So this is all happening because I have to meet one particle, have to meet one dark matter particle. Okay? And now the trick that we're going to do is that this number density of dark matter, we're going to relate this to measured quantities. Okay? So the way we're going to do this is by playing with redshifts. Okay? So let's play with redshifts. Okay, so to play with redshifts, let's remember the following fact. Okay, so our entropy, our total entropy S is conserved. Okay, and our total entropy is the entropy density times the scale factor cubed. And what we're going to do is use this to redshift. Okay, so basically what this means is that we can scale things with the entropy density, which is 1 over a cubed. This goes like t cubed. Okay, and also I'll just remind you, temperature scales like 1 over scale factor. Okay, so after freeze out, at the point where we're trying to, we need over here, right over here, what we're looking for, we want the number density of dark matter at freeze out, right? Now, after freeze out, number density is fixed. That's what we mean by, we're assuming instantaneous freeze out for this sort of back of the envelope estimate. And so what we're going to do is we're going to redshift back to figure out what is this number density that we need over here. Okay, so we're going to redshift all the way back to matter radiation equality. So redshift to T equality. Okay, this is at matter radiation equality, which is roughly at 0.8 eV. Okay, so this is what we're going to redshift to. And we're also just going to parameterize our cross-section. So this is a thermally average cross-section, ordinary cross-section, nothing that exciting. Let me just write it in the following way. I'll write it as some effective coupling squared over mass of dark matter squared. Okay, it's just a parameterization for this cross-section to sort of parameterize our ignorance. This is what a 2-to-2 cross-section looks like. And so let's see what happens at matter radiation equality. Okay, so at matter radiation equality, here's what happens. So matter radiation equality literally means that the energy density sitting in matter equals that sitting in radiation, right? So radiation sitting in matter, energy density sitting in matter at equality, that'll be the sum of the component that's sitting in the dark matter itself plus whatever's sitting in baryons. And this should equal the whatever's sitting in photons. Okay? Now here's where we're going to use the things that we know about dark matter, right? So we know that rho dark matter is roughly 5 times the energy density of baryons. Okay? And so what we're going to do here, and this is exactly the point, an example of where we're going to drop order ones. Okay, so what I can do is take this, and that tells me that at equality, roughly the energy density up to a factor of 6-ish, the energy density sitting in dark matter is ballpark that sitting in the photons. Okay, so this is where I'm neglecting. Let me just write that explicitly. We've neglected here order ones, but you can also see, if you wanted to walk through it, how you would keep these order ones too. Okay. You can already see though how to keep them. Okay, but there is an order one that we're dropping over here, and so we're going to now be able to take this and work our way through. Okay, so let's look at what we're interested in. We want the number density of dark matter at freeze out. Okay, so we're going to redshift from freeze out all the way to T equality. Okay, so this goes like the number density at T equality times, we're going to redshift with temperature. So here's my temperature of freeze out divided by T equality cubed. Okay, that's my redshifting to T equality. Now, number density at T equality is energy density at T equality divided by the mass. And I just copy T freeze out cubed over T equality cubed. And now we're going to use what we said, that the energy density in dark matter at T equality is of order that in photons at T equality. Okay, so this is going to go like the energy density in photons at T equality over m chi. And again, I just copy over Tf cubed over T equality cubed. And now we can use the fact that the energy density in photons is just temperature to the fourth. Okay? So I plug that in. So I'm going to have a temperature T equality to the fourth, but I have a T equality cubed downstairs, so I'll cancel those out, and we're left with T freeze out cubed times 1 factor of T equality divided by m of dark matter. And now instead of talking about temperatures, we're going to move to that variable x, which is dimensionless, mass over temperature. So let's move to that over here. I'll call xf will be x at time of freeze out. That's the mass of dark matter over the temperature at which it's freezing out. And so altogether, we can write this as T equality m chi squared over xf cubed. Okay? So this is our number density at freeze out, written in terms of T equality. And now let's go back to this equation. So let's give this equation up here a name. This was our equation. I'll give that, I'll call that star, okay? Which was saying, when is freeze out happening? When the rate for 2 to 2 is of order Hubble. So now let's go back and plug this into that same equation. And, okay, so let's compare it to our freeze out condition. So here's what we get. Our rate for 2 to 2, we said was the number density at freeze out times thermally average cross section, which we parameterized as alpha effective squared over m dark matter squared. Okay, now we're going to plug in this number density at freeze out that we just obtained. So this is alpha effective squared T equality. I'm going to have the m chi squared cancels out, and I have divided by x freeze out cubed. So this is the rate for the 2 to 2 process. And now we're going to demand that this is of order Hubble at freeze out. Hubble at freeze out is temperature at freeze out squared over m Planck. And again, we're going to move to this variable x, which, so we can write this whole thing as m chi squared over x freeze out squared times m Planck. Okay? So this is our freeze out condition. And what we can now do is just move things around and solve for m, the mass, as a function of the coupling. Okay? And if we do this, okay, so you see I have here, so just what we're doing is this versus this, and we're just shifting around to solve for m. And what we find when we do this is that m chi, dark matter mass, goes like this effective coupling times square root of T equality and m Planck. If I plug in numbers, this is roughly alpha effective times around 30 TeV. Okay? So this is the result for the WIMP. And what you automatically see over here is that it happens to be the case that if the size of this effective coupling is of order an electroweak coupling of order 10 to the minus 2, then the electroweak scale emerges. Okay? So if alpha effective is of order 10 to the minus 2, this is how we get the weak scale. Okay? But what I really want to stress here is that this is a coincidence of scales. Okay, there are two unrelated scales, m Planck and T equality, that contrive together to give a geometric mean, which, if we have a weak coupling, gives us the weak scale. Okay, this is the WIMP miracle, but you already see over here that it's really just a coincidence of scales, and that it just as easily gives you lighter dark matter or heavier dark matter, depending on the size of the coupling. Okay, and another way to write out this result, which maybe has some interface with how Josh might have written it. So I'll just write that out here. Another way to write this, of course, is just to say that the size of the cross-section that we need, which we called alpha effective squared over m chi squared, that this should scale like 1 over t equality m Planck. Okay, so there's a chance that you might have seen it in this way in Josh's lectures earlier in the school. Okay, this is just a different way for phrasing things for the WIMP. Okay, are there any questions on the WIMP before we delve into SIMPs?
Yeah, one here.
So what did happen with the variable xf? I guess we just assume it's of order 1.
Sorry, could you say that again?
In the last calculation, the variable x at freeze out vanished. So what happened? I guess we assume it's of order 1, or? So
yeah, well, as I said, I'm being sloppy here with order 1. So you can write this equation more accurately, including the factors of xf. xf, the temperature of freeze out, is always of order 20. We're going to show that. We'll solve it explicitly for the SIMP. It's because it's just a logarithm of parameters. It's always for many orders of magnitude, and almost every single process that people write down for dark matter. The freeze out temperature, it's always freezing out non-relativistically at temperatures that are roughly a factor of 20 beneath the mass. And you can follow through with that. If you try to plug in the exact numbers, the fact that I'm writing here alpha times 30 TV, I've already taken into account the exact x dependence. Yeah, but you can think of x as sort of an order 10 and order 20 factor, and you can track through properly, put that in, and all of the other order 1s that we've been neglecting over here. Okay.
Okay. Thank you.
Okay.
There's another question. Wait a second.
So hi, I missed why there is no gradient term in your Boltzmann equation.
Sorry, could you say that again?
Yeah, I missed why there is no gradient term in the Boltzmann equation which you have written up.
Why there's no
gradient?
What's
you
missing?
have the time derivative, and I was wondering why there is no. I mean, sometimes like you can have inhomogeneities on the density, and so then in that case you can have a gradient term in the left part of the in the Boltzmann equation.
Yeah, so well, everything I did here is super simple. Okay, so I'm not talking about any inhomogeneity. I'm just talking about sort of homogeneous universe. What's happening, just to sort of set the stage. So we're talking about a very simple scenario over here where we allow it to have collision terms. So we're not just talking about free particles, but this is a very simple form of the Boltzmann equation.
Okay, so in principle there can be a gradient term as well. Or not.
I'd have to think about that. That's not the typical way that that one writes out the. I mean, you see how we arrived at the Boltzmann equation,
yeah, sure,
right? So
sure.
I literally started off with 3 particles, so just no change of total number of particles, and then number of particles is density times. So this is really a time derivative equation. Now, of course, the real way that you write down Boltzmann equations, you start with phase space distribution.
Yeah, exactly. Yeah.
Okay. And then you can really, you can do things in a more accurate way. You can get, but for the purposes that we're doing over here, it's we can stay at the level of just talking about the number densities. But in a proper way, you'd really be working with phase space densities, and then working through everything, writing down matrix elements squared, integrating over phase space, and then things can become more complicated. But there's no need to introduce any complications for this story that we're interested in here.
Okay, thank you.
Okay. Okay, so if there are no further questions, then we're all set now to start talking about 3-to-2 interactions. Okay, so let's start over here. 3-to-2 interactions, these are going to be, oops, let's write it shortly, SIMPs, okay? So, and let me just give you some references for this. So this is work that I put out a few years back. So this is with Kuflick and with Tomer Volansky and with J. Wacker. This was a PRL. I'll give you the the archive number 1402.5143. And I want to stress, we came up with this idea, it's very awesome, on the beach. Okay, so I'm a strong believer of doing good physics while in good spirits and having a good time in beautiful locations. So I'm confident that you guys too can come up with incredible new ideas while at Les Ouches or other beautiful places. Okay, so here's how this goes. Until now, when we talked about, let's say when we did the WIMP right now, what we had was dark matter annihilating into something else, okay? So you could ask the question, and this is literally how we started thinking about this originally, what if what's important is not so much how dark matter talks with other stuff? What if what's most important is how dark matter talks with itself, okay? That's the question that we're gonna pose. What if most important is how dark matter talks to itself, okay? And so imagine, for instance, the situation where our dark matter is the lightest, let's say the lightest state in, I'll call it a nearly secluded sector, okay? And so you want to start talking about self-interactions of dark matter, right? How does dark matter talk with itself? So these are self-interactions to set the relic abundance. Okay, and so the first thing you might think of doing would be, okay, let me just stay with, 2 to 2. Here's chi goes to chi. Except this doesn't change the number of particles, right? This is just scattering the particles amongst themselves. It doesn't change the number densities. Okay, and so the first process that would change the number density in the early universe are going to be 3 to 2s. Okay, so the first process that does change the number density are these 3 to 2 processes. So here's 3 dark matter coming in and 2 dark matter shooting out. Okay, these are 3 to 2 processes. And of course, you could do higher orders as well, and we'll work through the parametrics of that shortly too. Okay, I just want to point out over here 3 to 2 processes. Notice that dark matter, if it's a 3 to 2 process, the dark matter is undergoing, dark matter can't be a fermion in this case. Okay, so dark matter has to be a scalar, otherwise this process won't be allowed. Okay, so in this case, dark matter is a scalar because of this 3 to 2. Okay. So if this number changing process is what's responsible for the relic abundance in the universe, we want to understand, very similar to the WIMP, what mass scale is involved, what temperature is it freezing out, what's the size of the coupling, okay, and how are these things related? So let's use our estimating tools that we've developed. Okay, so here's our process. Let's use our estimating tools. Okay. So I'll start by writing out what the Boltzmann equation looks like, but then we're really going to work through the back of the envelope estimate to understand when freeze-out is occurring. But here is the Boltzmann equation, dn dt plus 3hn, and this equals, I'm gonna write it out, and I'll explain in a moment how I got to this. So it's going to be minus the thermally average cross-section for this 3 to 2 object, and I'm going to call it in a funny way. I'm going to call it sigma v squared of this 3 to 2 process. Okay, it's just a parametrization for what sits over here. And then I'm going to have here n chi cubed because I have to have 3 particles meeting each other. And I'm going to have here minus n chi squared, n chi equilibrium. This is what the back reaction looks like, and you can work it through with detailed balance. We're going to see it explicitly when we work through the n to 2 case, so we're not going to do it over here, but if this is confusing to anybody, I promise you we're going to understand it when we look at the n to 2 case. Okay, so I'm just sort of going to put this over here. This is the full Boltzmann equation for this system. But as usual, because the same type of freeze-out picture is happening, we can use our back of the envelope tools to understand when is the freeze-out happening, assuming instantaneous freeze-out. Okay, so here's our here's our tools when our freeze out is happening. When the rate for this 3 to 2 process for these annihilations is of order Hubble, right? That's when the process can no longer happen, just like was the case for the WIMP. So now let's work through what is the rate for the 3 to 2 process. Okay, so the rate for the 3 to 2 process, just like the WIMP, it has two factors that feed in. Okay, the first is, remember, we always ask ourselves, I'm a dark matter particle. Who do I need to meet in order for the process to happen? So in this case, I have to meet 2 more dark matter particles, right? Because I'm 1. So I have here that the rate is proportional to the number density of the dark matter squared. Okay, so this first factor over here is because if I am a dark matter, I need to meet another 2. Okay. And the second thing that the rate is proportional to is the strength of that interaction, the thermally average cross-section. I'm going to call it sigma v squared 3 to 2. Okay. And I'll just explain this sort of peculiar notation. So this thermal average cross-section is just is sort of the strength of the interaction. Let me just explain this factor here, v squared. Okay, again, this is just sort of a standard notation. We put it in there because it's kind of like if I'm a dark matter particle, really there's a flux of two dark matter particles that are coming and hitting me. So you can kind of think of that as if that's NV. Right, the flux of one dark matter particle would be just NV, and so you need this squared. Okay, so that's sort of the reason for this type of notation, but it's just a stand-in notation for the collision term. Okay, and now what I also need to explain is what on earth is this weird 3 to 2 object. We're not really used to thinking of 5-point interactions or 3 to 2 types of interactions in our ordinary life in particle physics. So let me parameterize what is this sigma v squared. Okay, so this sigma v squared of the 3 to 2, I'm going to parameterize it in the following way. I'm going to call it alpha effective, again, parameterizing my ignorance, some coupling cubed, and I'll motivate the choice of cubed a little later today, divided by dark matter mass to the 5th. Okay. Now, in terms of dimensions, this is correct. So if you look back, let's look at our Boltzmann equation over here. Then you see up here that here's our thermally average cross-section, and you see that it multiplies number density cubed. And so you can check out that in terms of dimensions, you end up here with this is really the right dimensions for this very weird object. But again, when we work through the N2 case and we go through detailed balance, you're going to be able to see exactly why this, how to understand the scaling dimension of this cross-section. Okay, but for now, this is just a parameterization for what this cross-section is. Okay, and now we take this and we want to understand how when is freeze-out happening. Okay, and so we do a very similar trick to what we did for the WIMP. We're going to take our number density of dark matter at freeze-out from the result that we've done before, okay, from our redshift to T equality trick. Okay. And so I'll remind you that what we got over there is that the number density of dark matter at freeze out goes like T equality m chi squared over x freeze out cubed. Okay. So we're going to use this and plug it into, let me give this equation a name over here. This equation here, let's call it, oops, we'll do it in red. So this is our, I'll give it a double star. Okay, this is the freeze out point. So now let's plug that into here. So we have that the number density, so we have number density squared, right? So that's going to be T equality squared m chi to the 4th over x freeze out to the 6th. That's my number density squared. Times thermally average cross-section, which we just gave it, we parameterized it as alpha effective cubed over mass of dark matter to the 5th. And freeze out happens when this rate that we've just written down is of order Hubble. Hubble is temperature squared over m Planck, which again we move to the variable x, and we get m chi squared, over x freeze out squared m Planck. Okay, so this is the freeze out condition. And again, what we do is we just shift things around and we solve for m as a function of the coupling. And when we do this, we find the following result. We find that m chi scales like alpha effective times t equality squared m Planck to the 1/3 power. And if you plug in the numbers, this comes out to be alpha effective times around 100 MeV. So this is what happens. This is what freeze out gives us if a 3-to-2 process is what's responsible for the relic abundance of dark matter. Okay? And so what you see over here, right, is that what we get now is that the relationship between we have mass goes like coupling times no longer an ordinary geometric mean between T equality and M Planck, but what we get here is some generalized geometric mean between T equality and M Planck. Okay? And now it happens to be the case that if this alpha effective, if this coupling is of order 1, is of order a strong coupling, then the strong scale emerges. Okay, so if alpha effective is of order 1, is of order a strong coupling, then the strong scale emerges. Okay? And so instead of a weakly interacting massive particle, where a weak coupling gave us the weak scale, now we have a strongly interacting massive particle, where a strong coupling gives us the strong scale. So instead of a WIMP, we called this a SIMP. So this is what's called the Simp Miracle. And what you see over here is that the mass that this predicts is substantially lighter than the case of the WIMP, right? The mass scale that you get over here, you see for exactly a strong coupling, you get of order 100 MeV, but this gives you masses for dark matter that are much lighter typically than the WIMP with stronger coupling, okay? And very different, because these strong couplings that we're talking about are not strong couplings to ordinary matter, they're strong couplings to itself. Okay, so this gives us much lighter dark matter than is typical for the WIMP. And importantly, very different interactions. Okay. So this typically gives dark matter masses between the MeV and the GeV scale. And in terms of the freeze-out picture, it's literally identical to what we had in the WIMP. So this, this picture that we're sort of used to thinking of for the WIMP, the freeze-out picture is really just remains the same. Okay, so the freeze-out picture is the same. What we've just worked out is what is the mass that's predicted for this process to be what's responsible for the relic abundance. Now, certainly an important question to ask is, at what temperature is this thing freezing out? Okay, so for a WIMP, the temperature's the value of X freeze out, mass over temperature, is typically of order 20. And let me show you what happens in this case. It's also, already give you the spoiler, it's literally going to be very, very similar. And you'll be able to see as we work through it exactly why, for all of the different processes that people think of, really things stay freezing out non-relativistically, roughly at factors of 20 beneath the mass. Okay, so let's work that out now. So what temperature does it freeze out? Okay, so what is the value of XF? So the way you think of this is sort of, you do instantaneous freeze out. Okay, so let's look at the point of freeze out. Let's assume that just before freeze out, everything is in equilibrium, and just after it departs from equilibrium. Okay, but at that point of freeze out, I could roughly assume that things are in equilibrium. And so here's my number density of dark matter, right?
Sorry?
The equilibrium distribution.
Can I ask
Is there a question?
Yep. Sorry. So since this is an interaction entirely inside the dark sector, does this avoid all indirect and direct detection experiments?
Well, we're going to talk in a moment. So right now, all we did was assuming just interactions entirely within the dark sector. We're going to talk in a moment about how I've been cheating, and that has to do with how it has to talk also very weakly with ordinary matter. But in the story that we've told so far, we've only worked out that we have strong self-interactions amongst the dark matter particles themselves.
Okay, and another question. We wrote the right for the 3-2 process, and I understand this has to involve the density square, because a dark matter particle has to find 2. But the reverse process, the 2-3, which I guess should also be considered, would have a different dependence. So, I mean, are we assuming that the 3-2 process is equal to the 2-3, or?
Well, in the regime, okay, so in the regime, this is, again, just think about the case for the WIMP, okay? Also for the WIMP, we always have the inverse process. Now we write, and you take into account in your Boltzmann equation both of these types of processes, okay? And the rate for them indeed scales differently, right? Also because a cross-section for 3-2 is different from the cross-section to 2-3. Also for the WIMP, the cross-section between the annihilation and the production is not identical. The way that you relate them is by using detailed balance, as we saw for the WIMP. And that enables us to write one cross-section and write down what are the factors that we need to have to capture both the forward and the back reaction processes in our equation, okay? And we've done that in, sorry for scrolling, over here, okay? And so we're going to work through, soon we're going to do the n-2 case, and then you're going to be able to see explicitly how we take into account these terms. But in principle, the second term, let me just underline that over here, this term over here, you see where I'm indicating in blue? That combined with this captures the back reaction process. Another way that I could have written it was thermally averaged 2-3 cross-section times number density of chi squared. These things are the same. We've just used detailed balance to write them together. And the reason that none of that matters when we're actually doing the freeze-out computation for our back of the envelope estimate is because at that point of freeze-out, we're in a regime where the back reaction has already rapidly, is really sort of shut off. And so really all that's happening for the most part is the forward production process of 3-2. Excuse me, annihilation process of 3-2. Okay, so we're in a regime where the 2-3 is essentially negligible. Does that make sense?
Yes, I see. Thanks a lot.
Okay.
One more question, sorry. Just 1 sec.
Yeah, so we've been talking about like a nearly secluded dark sector. Does it make sense to distinguish between the temperature of the dark sector and the stand model temperature, or like the freeze-out temperature, would it be related to T dark or T radiation?
Yeah, so excellent question. That exactly touches upon the point that I've been cheating. Okay, so in the way that we've done it so far, you're absolutely right. We've treated the temperature as if the temperature of the dark sector, the temperature of the rest of the universe of the standard model is the same, that I have one temperature that describes everything. And that, of course, in the absence of something additional, which I haven't yet described, wouldn't be correct, okay? We're going to also work through what happens if, indeed, there is no way to, if, indeed, everything that's happening is just what we've described so far. That's how we're going to get to cannibal dark matter. But we're going to talk about the part where I've been cheating you in a few moments. Okay, so let's hold back with that question for now. And if there's still confusion after we work through how I've been cheating you, then and of course I'm going to show you why it was legitimate why the cheat was okay. Then please ask again. Okay? You're absolutely right. In the way that we've done it so far, there's something that doesn't entirely make sense.
Thank you.
Okay. Okay. So let's talk about what temperature we're freezing out at, okay? So what is the value of XF? Let's assume and make sure it's consistent that we're freezing out non-relativistically, okay? So here's how it goes. So our number density, if I'm non-relativistic, the number density is the mass times the temperature to the 3/2, and we have the exponential suppression, e to the minus m over t. Our rate we said is proportional to two factors of number density, right? So here's n chi squared. That means I'm going to have here mass times temperature cubed, e to the minus 2 m over t. And now let's write out our freeze-out condition, okay? Remember, we called our freeze-out condition these 2 stars. Here it is. So we have number density squared times this thermally averaged 3 to 2 cross-section. And this now I can write out as mass times temperature cubed, e to the minus 2 m over t, times my cross-section, which we called alpha effective cubed over m chi to the 5th. And our freeze-out condition requires that we demand that all of this is of order Hubble, which is t squared m Planck. And again, we move to this variable x, which is mass over temperature. So this is m chi squared, over x freeze-out squared m Planck. Okay? And now we want to solve for x. Okay? But what you see, what's happening over here? X appears, ordinary in a polynomial way, but up here it appears inside the exponent. Okay, what's sitting here is minus 2x freeze out. Okay, and so what this means at the end of the day is that when you solve here for x, you get that x freeze out goes like, I don't know, minus a half logarithm of all these parameters. Okay, and you can work out the exact form of it. Okay, but this always stays in the ballpark of 20. Okay. So you see over here, if I was going to take a WIMP, I'd have only one factor of n. My cross-section would scale differently, but it doesn't make a difference because the fact that it's freezing out non-relativistic is going to give me an exponential. And so up to an order 1 sitting inside the exponential, which just is an order 1 inside the logarithm, it makes no difference. Okay? So we always get that the freeze-out temperature is logarithmically dependent on all of the parameters. It's roughly of order 20. Okay? So dark matter freezes out non-relativistically at temperatures that are roughly a factor of 20 beneath its mass. This is true for the Simp, and this is true for the WIMP, and this is true for all of the other 2 to 2 zoo processes that we wrote up before. Okay, so this is when dark matter is freezing out. Now, as promised, I'd like us to work through the more general case, not just of 3 to 2, but of n to 2. Okay, and also sort of understand some of the scalings that come out from that. So here we are. More generally, let's look at n to 2 processes, okay? Because, for instance, maybe the dark sector has a Z2 symmetry, okay? And then I can't have 3 to 2 processes happening. So, maybe there's a Z2 symmetry. Maybe my dark matter is a fermion. All right, so there could be many reasons why a 3 to 2 process wouldn't be allowed. And in that case, we'd have to go to some larger n to 2 process. So let's take a look at what happens in this case. So here's the process. I have 1, 2, particles 1, 2, all the way down to n. Something's happening, and 2 particles are coming out. Here's my n to 2 process. Okay, and these are entirely self-interactions. Okay, so every particle in this process is a dark sector particle. And so let me call the thermally average cross-section, and again, inspired by that notation of how many particles I need to meet, so how many fluxes that carry factors of velocity I have to have, let me call this sigma v n minus 1, because if I'm one dark matter particle, I have to meet n minus 1 dark matter particles for this process to occur. So let me call that thermally average cross-section of the n to 2 process. I'm going to parameterize it as some coupling to the power of n divided by mass dimensions of dark matter of the following form: 2 plus 3 n minus 2. And now let me show you how I know this is the right dimension. Okay, so let's work through detailed balance. Okay, so I remind you that detailed balance says that forward processes equal backward processes in equilibrium, because in equilibrium they should be canceling. Okay, so forward in this case is n to 2, and that has to equal the backward, which is the 2 to n, when things are in equilibrium. Okay, so let's write that out. So that means that if I think of what are my collision terms sitting on the right-hand side of my Boltzmann equation, that so from the one hand I have number density in equilibrium, n particles are meeting times the thermally averaged cross-section for this n to 2 process. And I have, from the flip side, I have the 2 to n process. So that's where I have n equilibrium squared times sigma v 2 to n. Okay, and this, everything is in equilibrium. So this should equal 0. Okay? Does everyone understand how this is the collision terms? Okay. So the advantage of writing it this way is the following. So now let's solve what is the thermally averaged, what is this weird object? Okay, this n to 2 cross-section, which is kind of wacky. We're not used to thinking of this, okay? Because it's not really a cross-section, right? This equals 2, so what I have is n equilibrium, and I have over here to the power of 2 minus n times an ordinary cross-section, sigma v, of the 2 to n process, okay? So sigma v of the 2 to n process, that's an ordinary 2 to something cross-section. That's literally what we learned from Peskin and Schroeder in our first year of graduate school. You know what a cross-section is. That's the cross-section that has an ordinary dimension 1 over mass squared. Okay, so let's just write out mass dimensions over here. So this part, nothing special over here. This has mass dimensions minus 2. Okay, and what's this guy? Well, this guy is number densities. That's dimension 3 to the 2 minus n power, right? So this is giving me mass dimension 3 to the 2 minus n. Okay? And so combined, what this tells me is that this weird n to 2 object that we've been talking about, this whole thing has dimensions that are mass to the minus 2 plus 3 and minus 2. Okay? And that's why I knew to write this dimension over here. Okay? Okay, so now that we have our weird n to 2 cross-section that we've parameterized in a way that dimensionally is correct, let's write out what is our n to 2 rate. Okay? So for an n to 2 process, if I'm a dark matter particle, I have to meet n minus 1 guys. And so this scales like number density of dark matter to the n minus 1 power, and times the size of the interaction cross-section, which is this sigma Vn minus 1 n to the 2. Okay, and of course we require, as usual, that this should be of order Hubble. And so, again, using the exact same trick as we've done now a couple of times, where we should redshift to T equality, what we find, and we plug in the parameterization, and we solve for mass as a function of alpha, what you find now is that m chi scales like that coupling times T equality to the n minus 1 times m Planck, all of this to the 1 over n power. Okay, so this is the general scaling of how dark matter mass relates to coupling, to self-coupling, for self-interactions of n to 2. Okay, and just to make sure we're all on the same page, you see this n minus 1 factor over here of T equality. That's because in the way that we've related number density of dark matter to measured quantities, each number density carries 1 factor of T equality. Okay. So each number density of chi has in it 1 factor of T equality. Okay. And so if we didn't want to do a 3 to 2 process and we wanted to do a 4 to 2, so let's just work that out. For instance, if I take n equals 4, so 4 to 2 processes, what you'd find is that the mass of dark matter scales roughly like alpha times around 100 keV. Okay. And in a moment, when we talk about how I've been cheating, you'll see why this is potentially more difficult for a more difficult realization of this mechanism, because it's a little bit problematic for dark matter to be in kinetic equilibrium, as we're going to see, at temperatures that are with masses that are of order 100 keV. But as you go higher and higher in n's, you are pointed to lower and lower dark matter masses. Okay. Now, I'll also just point out that, of course, n to 2 processes are less familiar than the ordinary 2 to 2 that we're used to thinking of. So let me just give you here quickly a toy model, and later tomorrow we're going to see a full theory. When we talk about dark sectors. Okay, but let me at least provide you here with some with a toy model. So for instance, for 3 to 2. Let me give you a toy model. It's a toy Z3 model, okay? So imagine that you just have some single scalar. Okay, so I can have chi cubed interactions, and I can also have absolute value of chi to the fourth types of interactions. Okay, so in this toy Z3 theory, I have 3-point self-interactions and 4-point self-interactions. And so you can figure out how do I need to glue these things together in order to get 3-to-2 interactions. And there are actually two ways. Okay, so one is to glue together 3 3-point interactions. So that'll look, let's say, something like this. Here's one 3-point interaction, and here's another 3-point interactions, and here are two that are shooting up. Okay, that's one way. Or I could take one 4-point interaction and latch on a 3-point interaction. Okay, so these are sort of two different topologies for how I would get 3-to-2 processes. Okay, and this one where I have here 1, 2, 3 vertices is the one that really inspired our parametrization of the 3-to-2 cross-section as a coupling cubed. Okay, so this is really what inspired the parametrization of the alpha cubed in our cross-section for the 3-to-2 process. Okay, but you see that, you know, in general, you can do this in many different ways. So over here we can have 3-point interactions, or one 3-point plus one 4-point interaction. Okay. And in general, as we'll see when we talk about dark sectors tomorrow, these parametrizations for the cross-section, which, you know, we've used to understand what's the relationship between mass and coupling, you of course can cast it into the particular language and parameters of any model that you write down that realizes these mechanisms. And we'll see explicitly how that happens tomorrow. Okay, so we've worked through the scaling of mass and coupling, and what's predicted for self 3-to-2 interactions, and now we've also done in general n-to-2. And now, as I've said, we have to address the fact that I've been cheating.
So
okay.
There's a question in the chat. Maybe Joseph want to speak up?
Sure, just a moment. Question in the chat, sure. Why only, in this particular...
Well, so let me read this for the people here. So could you explain a bit more why only those two reactions are possible?
Sure. So, so if I have a scalar that has that have a Z3 symmetry, okay? So I can't write down, you know, I can always write down absolute value of something squared, right? So first it's a scalar. I'm only writing down a renormalizable theory. So I can have a chi cubed because that respects a Z3. And I can have a chi to the fourth when it's absolute value because that's also going to respect my Z3 symmetry, okay? And if I have these types of, you know, what I take from this is that basically my building blocks, right? Anytime I write down a Lagrangian with interactions, and I write down from that, you know, visually, what are my vertices look like? What are the building blocks that I can play with? And now I start to glue them together to understand what types of processes I can write. These are my two building blocks for interactions. Something that has 3 legs and something that has 4 legs. Okay, and I can figure out how can I attach them together to get leading order contributions to particular processes. And so for the 3-to-2 case, if these are my two building blocks, my 3-point and my 4-point vertex, this is the way that I can glue them together in order to get 3-to-2 interactions. Okay.
May I also ask a question? Would it make sense to look also to N to M processes?
Yeah. So obviously, what I'm doing here is definitely somewhat simplified because you can certainly you don't have to do just n to 2. You could do n to some other number that's smaller, and you can work out what the scaling is. These are definitely things that you can do. You see that from the perspective of like the scaling, you already see how things are going to behave, right? How many factors of number density I have, that's determined by the n to some, right? By the n, the initial state for that process. But what would change is going to be the dimensionality of your, the dimensionality of that cross-section, okay? So that's something that you, in principle, have to work through. Again, you could do this through detailed balance. Maybe I'll decide you can also do this even more easily, not even working through detailed balance, because the rate, you know that the rate goes like the thermally average cross-section for whatever, whatever weird dimension thing you're writing down, times n minus 1 factors of number density. And because that's a rate, you know that at the end of the day, whatever combination you're writing down has to have dimension 1, right? We compare that to Hubble. Hubble has dimension 1. So that already feeds back to tell you what's the size of that cross-section. What's the dimension of that cross-section? And when said that way, you already see that actually the dimension is the same. So you're gonna get a very similar answer, but certainly when you go ahead to write down models, you have to think about all of the different processes of that sort that could be contributing.
Okay, thank you.
But yeah, maybe I'll just say in general that if there's one, like, I think the big picture that I hope that you take away from the school in general, but definitely from my lectures, is not specifically to be to be like experts and simps or experts on elders or experts on cannibalism. It's to give you the tools to think outside of the box, because for so many years people were thinking in a very particular way. And when you just realize, if you just ask yourself, can it be this? Can it be that? And the answer is usually yes. And you just have to work through it. And hopefully I'm going to be giving you tools to be able to explore that, and for you guys to write, the next amazing mechanism that hopefully contains a crocodile in it. And more hopefully will be the one that really explains the relic abundance of dark matter. Okay. Yeah. Okay. Yeah, so I'm gonna come back to slightly more mundane statements now. Another question?
Yeah. Well, in the second case, when you combine the 3-point and the 4-point, does this change the scaling in alpha? Like you will have not a single alpha effective, I guess, right? You will have two coupling constants, which will control the mass.
Yeah. So I wanna absolutely. I want to draw a very distinct differentiation between what I'll call, let's say, the mechanism level, okay, versus model realizations, okay? What we've done so far, up until writing down this toy model, this is the 3 model, is work at a mechanism level. And over there, I parameterize my ignorance of what particular model and parametrization and couplings exist in the theory that give me a 3-to-2 cross-section, okay? And I just call that cross-section, I give it a parametrization. I was actually careful even, I don't call it alpha, which might sound like as if it's a particular coupling. It's some effective coupling, okay? It's a way to parameterize my ignorance. Given that parametrization, there's a relationship between mass and that effective coupling. Now, at the end of the day, once you figure out from the mechanism level what type of theory, what type of masses, et cetera, you're expecting, now you, of course, have to go ahead and try to find particle theory realizations of these mechanisms. And we're going to do that. We're going to work through that tomorrow. And this toy model is one simple example of that. And certainly once you do that, your theory has its own couplings, its own parameters. And what you can do, though, is the reason that the mechanism level is still so important is because you can take the computation in your theory. You're going to compute, as you said, you have your 2 couplings. You're going to compute the sum, the amplitude for the 3-to-2. You're going to have the matrix element squared. You're going to integrate over all of the phase space to get that effective 3-to-2 cross-section. And it's going to have some dependence on the parameters of your actual theory, okay? But you can still relate what's the size of that cross-section to the size of the cross-section that we obtained at the mechanism level, okay? So you're absolutely going to be casting our results into the language of the parameters of your theory, okay? We're going to see how to do that explicitly tomorrow in some particular dark sectors, but that's absolutely sort of the way that the process goes. There's no longer some effective coupling here. That was a way that we used before we had a model to parameterize what's going to happen.
One more question here.
Yeah, very quickly, with this set 3 symmetry, why don't you have semi-annihilations?
Well, you can work out, so that's in the theory that I've written down over here, all I have is a scalar, so I don't know what you mean here by semi-annihilations, because there's only one particle that's here. Once I couple it to the standard model, you can work out that everything works out well. But maybe the Z3 was meant to be like a little helpful, because often people, certainly when I remember when I was starting my postdoc and we first put out this paper and I gave a talk at some very fancy university, and then the first question that came up was like, oh, but like the 3-to-2 processes, like who can even write this down? And the answer is it's very easy to write down. So that's mainly what this is meant to address. And I'm going to show you guys tomorrow that it's actually so easy to write down. It even happens in the standard model itself. Okay. But if the Z3 you find more confusing than helpful, then you can just shut it, shut the Z3 in a little box and put it on the side, and we'll talk about more complicated theories tomorrow.
Okay. Can you give an example of a 3 to 2 process in the standard model? Because 2 to 3,
yeah,
there
but
are many.
that's gonna be that's gonna be it's through something called the Wens-Domino-Witten term, and we're going to be talking a lot about that tomorrow. Okay, so let's hold on to that question for our lesson together tomorrow.
Okay, thanks.
Okay, so just to finish up the last piece for today is, as I've been saying, and there have been several questions, I want to address this. I have been cheating. I have been cheating you. Okay, which is not a nice thing to do, but I'm going to explain why it actually was okay. So in the entire analysis that we did, as was pointed out by a couple of you already, we've implicitly assumed that there's one temperature that I can write down that governs the entire system. Okay, so we've implicitly assumed one temperature for the entire system. Okay, now of course, if all we really had in the universe was 3 to 2 interactions of dark matter, then this 3 to 2 process pumps heat into the system, right? Because I take 3 guys who are cold, and the ones that are shooting out are each more energetic. They're hotter than the ones that are coming in. Okay, and this is something that's in principle problematic for structure formation. Okay, and so there has to be a way to cool. There has to be some way to dump the entropy between this sector into something else. Okay, so we need to be able to cool to dump the entropy. Okay, and the way that we can do this is, we could dump the entropy into some other light state. It could be a dark state, or into the standard model. Okay, so this can be into another light state, or the standard model itself. So for instance, let's look what happens if we exchange heat with the standard model. Okay, so on the one hand, I want to be able to cool. Okay, here's how I'm going to cool. Dark matter is going to scatter off of standard model particles. Okay, I'm dumping entropy. I'm shedding heat. And this is a process that is cooling. Okay, but at the same time, if this process is happening, then I have to worry that, again, I take this diagram, and like we saw in the WIMP, I'm just going to turn it now on its side. Okay, and then I have this process that can happen. Chi, the standard model. Okay, so this process would be annihilating. But of course, I don't want this process of annihilation to be happening, because I don't want that to be controlling the relic abundance. Then we're just back to the WIMP, and we haven't done anything new. Okay, so the question is, can we cool without annihilating? Okay, can we cool without annihilating? And a priori, you'd think that the answer is no, right? Because the cross sections between these two processes are very similar. But fortunately, as hopefully you realize by this point, rates are not just proportional to cross sections. Rates are also proportional to number densities. Okay, and so for this process over here on top, I'll call this the kinetic process. Then while it scales with some cross section, which also the annihilation process scales with, okay, and those are pretty similar, because rates are proportional to number densities, we have a very different scaling here. So when I'm talking about cooling, here I am, the dark matter particle. I have to meet a standard model particle. Okay. Okay, my children are home. Thank you, Lear. Thank you, sweetie. Sorry about that. So the rate is proportional to the number density of standard model particles. Okay. And in the annihilation case, if I'm a dark matter particle, I have to annihilate with another dark matter particle. So my rate is proportional to number density of dark matter. Okay, and these can be very different, right? So if we think about, can I cool without annihilating? The answer is yes, because I'm proportional to very different number densities, okay? So let's look at what that number density ratio looks like. So can it be done? Can we cool but not annihilate? So let's look at that, the rate for annihilations versus the rate for the kinetic process. That's roughly going to go like the rate of the number density of dark matter over the number density of standard model particles. And so if we scatter off of light standard model species, okay, electrons or photons or neutrinos, particles that are abundant at the temperatures that we're talking about, then, right, so let's write this down here. If I'm going to scatter off of abundance particles, okay, so electrons, photons, or neutrinos, then number density of dark matter is exponentially suppressed, while number density of standard model is not, okay? And so this ratio is very, very small, of order 10 to the minus 8, okay? So we can easily cool without annihilating, just like we wanted, okay? So the key is to scatter off of light standard model species, okay, that are abundant. And this is exactly what I mentioned at the beginning of our lesson today happens for the WIMP, okay? Also there, the reason that elastic scattering shuts off well after the annihilation is exactly because of whether you're scattering off of a relativistic abundant particle or non-relativistic particles, okay? And so we've now arrived at a set of conditions such that everything is working, okay? So on the one hand, we want the kinetic rate to be active at freeze-out. So compared to the 3 to 2 rate at freeze-out, we want this to be active. We want it to be large. And simultaneously, we want to make sure that our annihilation rate compared to 3 to 2 is small, okay, at freeze-out, okay? And so if we parameterize the way that these two sectors, the standard model and the dark matter, are talking to each other, so let's parameterize our Simp standard model interactions. Let me call this sigma v of the kinetic process, which is of order the same thing of the annihilation process. Let me call this sum epsilon squared over m chi squared. Okay, it's a 2 to 2 cross section. I'm just assuming that there's some small coupling epsilon between the two. Okay, so you kind of think of this pictorially, like here's my dark matter, and here's my standard model, and there's some small epsilon coupling between them. Then these set of conditions define a range of epsilon, a range of this interaction strength, such that everything is kosher, that everything works, okay? So we're just going to write this out, and then we'll finish for today. So there's a range for epsilon where everything works, okay? And so it roughly looks like this. Here is epsilon as a function of dark matter mass. And there's some two curves, I'll call them epsilon min and epsilon max, between which everything is fine. So here's epsilon min, the minimal value. It roughly goes like alpha effective to the 1/2 power times T equality over m Planck to the 1/3. And we have also a maximal value of epsilon of alpha effective times T equality over m Planck times 1 to the power of 1/6, okay? So these are these two curves. So here's, if epsilon is too small, then there's no kinetic equilibrium. We're not dumping the entropy, no good. If epsilon is too high, if we're up here, then this is where 2 to 2 takes over. So we're back to the case of the WIMP, and we haven't done anything new. But in between epsilon min and epsilon max, there's an entire range where everything is working, and this is the viable range for SIMPs. And to give you a sense of the fact that this is not some tiny range, just to give you some numbers. So for instance, if I look at dark matter masses, let's say up to 100 MeV. Let me do that in a different color. Sorry, guys. Let's make that in orange. So if this is 100 MeV, and let's say going down over here to the MeV scale, then epsilon here can be as small as 10 to the 11. Over here, we get to like 10 to the -9, and all the way here we're up at like 10 to the minus 5, okay? So there's a broad range over which the value of epsilon doesn't matter, but as long as it's in that range, everything is working, okay? So that'll be the last thing I'll say, that as long as epsilon is in between these two curves of epsilon min and epsilon max, its precise value doesn't matter. And what we get are these strongly interacting massive particles. Okay, so that's all I wanted to go through today. And our plan for tomorrow, we're going to be talking a little bit about what happens if the order between these elastic scattering, this entropy dump, versus the 3 to 2, who decouples first? What if it's reversed? We're going to learn about cannibals, about elders, and then we're going to dive into some dark sectors, QCD-like theories, and we're going to see how these types of mechanisms that maybe seem a little exotic are actually completely non-exotic and can easily be happening in QCD-like theories. Okay.
Okay.
And happy for questions. I saw there was a raised hand before.
Yeah, there was a raised hand, but we are a bit late, and we have the COVID tests waiting for us, plus cookies. So maybe it's better if we thank Yonit very much again, and we start again tomorrow at 11. Thank you very much.
Thanks, everyone.